Okay, so currently we are solving for plume velocity and other plume parameters. So far we have already derived a formula for plume velocity, which consists of W max uh, and this Gaussian profile, right? So in the last lecture we did dimensional analysis and also scale analysis to find this particular equation, which is the vertical velocity of the plume at different radial and vertical axes. And the formula looks something like this, where w is a function of r and z, and it is written as alpha b to the power 1 by 3 divided by z to the power 1 by 3 and multiplied with exponential of minus r square by capital R square. Okay, where b is same as b naught, that is the source buoyancy flux, and alpha is a constant, r is the supposedly the radius of the plume, which we have to find out, and rz are the coordinate system. Okay, so now having derived the velocity profile or formula for the velocity, we can use this formula to derive other parameters, which includes the volume flux. Next we do is q, which is function of rz, that is the volume flux of the plume. Then we will do z rz, which is the reduced gravity of the plume, and then obviously r, which is the radius of the plume. Okay, and why we are trying to find volume flux and reduced gravity, etc.? Because we have already seen that as plume rises up, right, it grows up, it entrains ambient fluid in itself, right? There is mixing between the plume and the ambient fluid, and that is why the volume that is going from here, that is, let's say, q naught, and the volume that we have here is greater than q naught. So q of z is greater than q naught. Okay, and likewise, if there is g prime naught here, and here we find z prime z, so z prime z will be smaller than z prime naught. Why? Because again there is mixing, so the temperature difference or constant difference between the plume and the ambient is decreasing as we go away from the source. So let's start with volume flux derivation, and we will find reduced gravity after that, and also the radius. In case of volume flux, I think we should not write it as a function of r and z, because this is defined as the flux per unit area, and that's why we can write it as q as a function of z only. Okay, and g prime can be defined as a function of r and z, but that also we will try to define as mean reduced gravity for the plume at particular elevation. Okay, so now let's consider this case where we have assumed that there is this influx of another density fluid, and that is forming a plume, and q here is q naught and q here is q of z. And if you look at this plume from the top, so this will look something like this. Top view of the plume at any cross section. So it will have different velocity, obviously, right? Because this has w here will be function of r and z, and w is in vertical direction, right? So now if we want to find the total volume flux, we have to find, we have to integrate the vertical velocity from radius r equal to 0 to the maximum radius. Okay, so for that we will, let's assume this is the plume center. We will consider a small element. Okay, where this is r and here it is dr. Okay, and we assume this is the plume radius capital R, and here we have w, which is function of rz. So to find the volume flux, volume flux at any z must be given as w, which is function of rz, 2 pi r dr, and it should go from 0 to infinity. Okay, so what we are doing here, we are defining one very small element of thickness dr, which is in the cross section of a plume at any particular elevation. So let's assume that this cross section belongs to a particular height, which is let's say it z here. Okay, so that belongs to that particular height z, and what you see in the left is the top view, and what you see in the right is the side view, right? And now we are trying to find the volume flux at any z. So we have to integrate w multiplied with 2 pi r dr, because that is the small area, and we need to integrate from 0 to infinity. And why infinity? Infinity because we cannot define a sharp boundary between the plume and the ambient, right? So we are not able to define a sharp boundary, and that comes from the Gaussian profile model we are considering, where if you remember, the velocity profile at any z looks something like this, right? So this is your the vertical velocity, which is maximum here at r equal to 0, but it tends to 0, wr tends to 0 as r tends to infinity, right? So wr becomes 0 only at r equal to infinity, and that is why we need to integrate velocity from 0 to infinity to find the volume flux. All right, so now we will put the formula for wr here, which can be given as, so 2 pi r, where wr is alpha b to the power 1 by 3 z to the power 1 by 3 e to the minus small r by capital R dr. Okay, where the middle term is this wrz. Okay, and we are trying to integrate it from 0 to infinity. All right, so here we know some of the terms are constant, so we will take the constants out, which are 2 pi alpha. B is also a constant because it does not change with height, and z is a constant because this integration is with respect to r. Okay, so 0 to infinity r e to the power minus r square by capital R square dr. This is what we are left with. Okay, so b is a function of z only, so b is not a function of R, and that's why B has come out. And also Z is an independent axis, so Z is not a function of R. Okay, and that's why B and Z are outside the integral. All right, so here we define another parameter which is dimensionless, that is eta, and we say this is equal to small r by capital R. Okay, so this simplifies our equation, that will become 2 pi alpha b to the power 1 by 3 z to the power 1 by 3 0 to infinity, and eta is so we replace r with capital R eta, and e to the power minus eta square, and this becomes capital R eta. Okay, where we take capital R out, because this is again not a function of a small r, so this becomes eta minus eta square d eta. All right, so this is what we have got. And now if you integrate this particular term, okay, that is eta e to the power minus eta square d eta, so this will give you a value equal to 0.5. so this has a fixed value that is equal to 0.5. okay, so if we do that, this actually gives us an equation of the form, this 0.5 cancels with 2, so this becomes pi alpha b to the power 1 by 3 z to the power 1 by 3 r square. Okay, now this r square that we have is the radius of the plume, so now this is something that is little controversial or self-contradictory, because we just said that plume velocity does not become zero except at infinity, and then we are defining plume radius, and by plume radius we would mean that beyond plume radius the velocity is zero, right? So here we assume that so this parameter is particularly found using lab experiments, and there is some threshold defined beyond which the velocity is assumed to be zero, and within which there is velocity or there is plume. Okay, so in this case, when we consider, let's say this is plume, we will assume that we will assume a straight line which is considered as plume, and outside is ambient. Okay, so this is for practical purpose, it is defined as a radius, but in reality or mathematically the velocity should become zero only at infinity. So this is a very blurred interface between the plume and the ambient, right? So we will still assume this is r, which is increasing with z. Okay, and experimentally it is found that there is an angle theta between the center line and the plume shape, so that theta is equal to 8.9 degree, that makes tan theta as 0.157. so that actually tells you that r by z is 0.157, or in other words r is increasing with 0.157 times z. Okay, where this is 7 and this is z. Okay, so r is increasing linearly with z, and this is found experimentally. What you see here are the experimental values. All right, so we now know r as a function of z, and we are considering this radius based on experimental parameters where we define a threshold, and beyond the threshold we assume that that's ambient, and within the threshold that is the plume. Okay, and also experimentally this alpha value is also found to be equal to 2.14 experimental value. Okay, so now we have got alpha and r as a function of z, so we can write q of z as a pi alpha b to the power 1 by 3 z to the power 1 by 3, and r square can be written as 0.157 z square. So these actually gives us where pi can be written as 3.14, alpha can be written as 2.14, and 0.157 comes out. So this becomes 1 by 3, and z to the power 2 plus 1 by 3, so that becomes 5 by 3. Okay, so q of z becomes finally equal to 0.157, sorry, not 157, this is equal to 0.167 b to the power 1 by 3 and z to the power 5 by 3. So this is the volume flux of the plume at a particular elevation. Volume flux of the plume at a particular elevation z from the source. Okay, so this is how the volume flux of the plume is found once you know the velocity. All right, and now we know the volume flux, we can also find the reduced gravity and the radius of so radius we already defined, we now want to define the reduced gravity. And one thing you see here is volume flux is actually increasing with z, it's increasing with 5/3 power of z. Why? Because there is continuous entrainment into the plume from the ambient. Right, now we will try to find the reduced gravity of the plume. So actually reduced gravity is a function of rz. It is continuously changing in both vertical and horizontal coordinate, but we will only define g prime bar or average reduced gravity for a particular height z for the simplicity. Okay, so what we will do here, we will assume that this is equal to 1 by pi r square 0 to infinity g prime rz, which is again multiplied with 2 pi r dr. Okay, so similar to volume flux, if we know g prime value at particular r and z, we can integrate and that will give us g prime bar. But now we have found only the vertical velocity but not g prime value at individual r and z value, and that's why we'll use another approach to find g prime bar. So recall that b is equal to b naught is constant, and what is b? That is the buoyancy flux, right? Buoyancy flux is a constant which is defined as b naught is q naught g prime naught, and b is defined as q of z into g prime z, where g prime is now an average value at that particular elevation, and that is why we can find g prime bar as a function of z using our B naught value. So B naught over Q of Z, or which is simply equal to B over Q of Z. Okay, so if you know Q of Z and we know B, we can find G prime bar. All right, and we already have found Q of Z, which is written here. So now to find G prime bar as a function of Z, we divide this by 0.167, B to the power 1 by 3 and Z to the power 5 by 3. And this gives us G prime bar as 6.08, B to the power 2 by 3, Z to the power 5 by 3. Okay, so this is the G prime bar value we get. G prime bar as a function of Z, which is simply equal to okay, so this is the mean reduced gravity of the plume at a distance Z from the source, right? So and you can see how G prime value is decreasing with Z. It is decreasing with 5/3 power of Z, whereas volume flux increases with 5/3 power of Z. And why is it happening? Because we have discussed it several times that there is entrainment happening from the ambient into the plume, and that is why the volume of the plume increases as we go away from the source, whereas the reduced gravity of the plume decreases as we go away from the source, right? And that is shown here in this equation, right? And now G prime might be little difficult to relate to real problems, so we can always convert G prime into the concentration or temperature difference. So G prime bar is also equivalent to G beta delta C, or G prime bar is also equal to G alpha delta T. So this will give you delta T as G prime bar by G alpha, and this one will give you delta C as G prime bar by G beta. So what are delta C and delta T? Delta C is delta C, we can write this as a function of Z, likewise delta T can be written as a function of Z. Okay, so delta C as a function of Z or delta T as a function of Z are the concentration or temperature difference between the plume and the ambient. Okay, so this is something we know, right? That delta rho, which actually creates G prime, which actually gives us G prime value, that is the reduced gravity, that comes from delta rho, and delta rho actually comes from either delta C or delta T. So if you know G prime value, indirectly you know the delta rho value, right? That using that you can find your delta C or delta T, which is a difference of concentration between the plume and the ambient, or difference of temperature between the plume and the ambient. Okay, so these equations can be used to convert G prime into delta C or delta T. Okay, so now we have found volume flux, reduced gravity, and radius of the plume. So if you want to plot it and see how it varies with Z. So let's say this is your Z axis and this is your plume where you're injecting, which has initial Q naught or G prime naught, etc. Right? So your Q, if this is how your Q naught will, Q of Z will look like. So let's say this is your Q naught value. So this will be your Q of Z, which is actually increasing with Z to the power 5 by 3, right? If you want to plot G prime naught, it will be something like this, right? It will look something like this, where this is G prime naught and this is G prime bar as a function of Z, which is decreasing with 1 over Z to the power 5 by 3. Okay, and likewise, if you want to plot your radius R, it again might, depending on what is your initial radius, this will increase with 0.157 of Z. Okay, that is which increases linearly. Okay, so these are different plots you will get. Radius will increase linearly in Z, whereas volume flux increases with 5/3 power of Z, and G prime decreases with 5/3 power of Z. Okay, so this is how your plume properties or plume parameters vary with distance away from the source. Okay, and this is all happening because there is continuous mixing between the ambient and the plume. Okay, and this behavior what we see here is valid only for unstratified ambient. So these are plume parameters in unstratified ambient, which means that rho ambient is constant. Okay, and now we will do plumes in in stratified ambient.